This isn't real.
What is real? How do you define real? If you're talking about what you can feel, what you can smell, what you can taste and see, then real is simply electrical signals interpreted by your brain.
Envision a universe immense and ageless, meticulously crafted to the minutest particle. Consider the intriguing notion of the simulation hypothesis, suggesting that our entire reality, from distant stars to everyday experiences, might be an intricate digital creation. The question arises, who or what is the architect behind this simulation? Around 12,000 years in the past, humans initiated the shaping of their environment, laying the groundwork for civilization. Fast forward to the present, and we find ourselves constructing virtual realms. Is it conceivable that an advanced civilization, potentially millennia beyond our own, has fashioned the ultimate simulation of our reality? Donald Hoffman, a cognitive psychologist and renowned science author with unconventional perspectives on reality, space, and time, challenges our common understanding. Hoffman asserts that our perceived world isn't the true reality. According to him, mathematical models rooted in natural selection principles suggest that our deeply ingrained intuitions might be deceiving. While many of us believe we see the moon as it truly is when we gaze up, Hoffman suggests that our perceptions could be misleading, as they are shaped by evolved intuitions rather than an accurate representation of reality. The existence of the moon, for instance, does not depend on observers. It would persist even without anyone to perceive it. While acknowledging that we don't perceive the entirety of reality, the prevailing belief is that our perceptions, shaped by natural selection, enable us to apprehend aspects essential for survival. This includes the conviction that our perceptions of space and time provide genuine insights into their actual existence, independent of observers. According to this perspective, objects like apples, chairs, the moon, quarks, and leptons would still exist with roughly the properties we observe, even in the absence of any observers. The adherence to the principles of evolution by natural selection leads to the conclusion that the language we employ to describe our perceptions, whether it's the language of space, time, shapes, objects, position, momentum, or colors, is highly improbable to be the incorrect language for delineating objective reality, whatever that reality may be. The issue extends beyond minor inaccuracies in perceiving the shape of a table or slight deviations in colors. The assertion is that no description utilizing the language of space-time, objects, and colors could ever capture the truth of reality. The argument posits that the nature of reality itself defies accurate depiction within the confines of this language. Thus, faced with a choice, one must either prioritize the acceptance of evolution by natural selection, one of our most robust scientific theories, or adhere to intuitions that regard space-time and objects as fundamental aspects of reality. The idea that reality can be an illusion is nothing new. Even ancient Greek philosophers, such as Plato, pondered the nature of reality. In modern times, these philosophical reflections have been transformed into a modern hypothesis, particularly influenced by advances in computer and digital technology. The simulation hypothesis. This hypothesis raises profound questions that challenge our understanding of being, consciousness, and the fundamental nature of reality. Delving deeper into this cosmic mystery, recent scientific discoveries give the simulation hypothesis a new dimension. An intriguing possibility arises. What if the laws of physics governing our universe are not just rules, but algorithms embedded in a vast cosmic program? This leads one to ponder whether we, the inhabitants of this universe, will ever be able to discern the digital underpinnings of our existence. Are we destined to exist without knowing the boundaries of programmed reality? In this simulated universe, physical laws take the form of algorithms, and our experiences arise from the computational processes of the advanced systems that simulate the model. Despite its speculative nature, this theory has attracted the interest of scientists and philosophers alike, generating both admiration and skepticism. A useful analogy to illustrate this concept is the scenario of the game Grand Theft Auto. Imagine that the participants in the game are located in different parts of the world, some in Canada, some in Europe, and some in China. during the remote version of the role-playing game. If one player, for example, notices a red Porsche to his right and reports it to the others, the participants in different locations can independently confirm the presence of the red Porsche, illustrating a shared simulated experience in a virtual environment. In this analogy, the participants in Canada, Europe, and China independently agree on the existence of a red Porsche, each rendering their own perception within the virtual environment. Behind this shared experience, there exists a coordinating reality, a world of circuits and software that remains unseen. A supercomputer serves as the orchestrator, receiving inputs from various sources such as headset directions and body movements, and feeding them into a model of the game. Within this model, there's a representation of the red Porsche, even though there is no physical red Porsche in the computer. The supercomputer coordinates the information and sends the corresponding visual data to the individual headsets, creating the illusion of a persistent reality of the Porsche for each participant. Despite the illusion of local realism, the analogy highlights that, in reality, there is no actual red Porsche for each player. Rather, it's a coordinated and simulated experience. While the headset is sophisticated technology, the supercomputer is notably more powerful. Similarly, the suggestion is that if we look beyond space-time, we will encounter a realm far more complex. Essentially, the assertion is that the scientific exploration conducted so far has been confined to studying the intricacies within our headset, namely inside space and time. The proposition is that a deeper and more complex reality lies beyond our current scientific understanding. As we embark on our initial explorations, we've acquired tools over the past 3 or 4 centuries, including experiments and refined mathematical theories, creating a symbiotic relationship between experiments and theories. Initially, we believed we were investigating objective reality, but it's now recognized that we were studying our headset within space-time. Today, we possess the capability to take preliminary steps beyond space-time, exploring structures that extend beyond it, and their manifestations projected back into space-time. Contrary to our earlier assumption that objects in space-time constitute the fundamental reality, this perspective may soon appear limited. Some scientists anticipate that in the coming decades, our current understanding will seem parochial. The notion that our reality is a simulation raises the possibility of detectable glitches or patterns betraying its simulated nature. However, identifying such anomalies presents a formidable challenge, given the ongoing evolution of our understanding of physics. A recent study introduces a novel proposition, an additional law of physics, a modified second law of thermodynamics, that aligns with the theory of a simulated universe. Central to this new law is the concept of entropy, a measure of disorder. While traditional entropy typically increases, the modified second law of thermodynamics posits that information entropy must either remain constant or decrease over time. The intriguing implication of this law is the optimization of information content in the universe, suggesting that the entire cosmos could be a highly intricate computer program operating on an unimaginable scale. Quantum mechanics provides compelling evidence for the plausibility of our universe being a simulation. The double-slit experiment, a cornerstone of quantum mechanics, illustrates that particles like electrons and photons exhibit characteristics of both particles and waves when not observed. This quantum phenomenon adds weight to the idea that the nature of our reality may be intricately tied to a simulated construct. In the double-slit experiment, particles exhibit a perplexing behavior by seemingly passing through both slits simultaneously, forming an interference pattern characteristic of waves. However, when observed, they behave like particles going through only one slit, a phenomenon challenging classical physics. In the context of the simulation theory, this peculiar behavior might find coherence. The rules governing the simulated universe may not adhere to our traditional understanding of physics. The observation effect in the double-slit experiment could be likened to a rendering feature in a simulation where elements are fully realized only upon observation. This is akin to how details in a video game environment are rendered when the player's character looks at them. Consequently, the assertion is that local realism is false, meaning that objects in space-time, such as a proton, do not possess definite values for their properties, like position, momentum, and spin unless observed. Additionally, local realism posits that these properties influence the propagation of information faster than the speed of light. This interpretation aligns with the outcomes of experiments like the double-slit experiment, regardless of whether we are indeed part of an elaborate simulation or not. These scientific inquiries serve as gateways to a deeper comprehension of our universe, urging us to reconsider the very nature of reality and our position within its intricate framework.